All right. So let's finish up our trilogy of lectures on analysis of functions. We're going to talk mostly about rational functions today. Well, rational functions as well as functions with fractional exponents and just other kinds of functions in general. Okay. Um, and then after this, for the rest of the chapter, we'll be talking about some of the applications of things like, maxima and minima and things like that, things of that nature. But for now, let's talk about rational functions and graphing rational functions. So we're going to build a lot on what you know about graphing rational functions from your algebra days, from your pre-calculus days. And some of you may have more experience with this kind of thing than others, so this ought to be fun. If there's anything here that you're not familiar with, then you've got to let me know, okay? But I'm going to operate from the assumption that you have some experience graphing rational functions, okay? So just to bring everyone up to speed, right? You may remember that rational functions have the form p of x over q of x, where p and q are polynomials. You may also recall that if you have a rational function, p of x over q of x, and p and q both have x minus c as a factor, then we can actually reduce the function, right? We can factor out that common factor and cancel it off. And then in that case, the graph of our original function f looks just like the graph of the reduced function, except that f is going to have a hole wherever you had that common factor, right? So it's going to have a hole at c, and then limit as x approaches c of f of x, right? So it's going to have a hole at that location. You know this from your pre-calculus days, even if you didn't use this notation to describe the point where the hole takes place. But this is the concept, right? Basically, you get this y value by canceling off the common factor and then plugging in c to the reduced function, right? But you just have a hole at that point. So on Desmos, it would look exactly identical because Desmos has a hard time graphing holes. Okay, so in Desmos, the original function and the reduced function are going to look exactly identical, but we know that actually you have a hole at x equals c. All right. Okay, so that's how you take care of a scenario when p and q have a common factor. So what we're going to do is we're just going to assume that p and q don't have common factors, because if they do, well then, you just plot the hole, okay? So we're going to assume that p and q don't have any common factors, and in that case, in pre-calculus, you graphed rational functions by doing a few things. One of the things that you probably did is you found intercepts. You found the x-intercepts, but the y-intercept as well, is usually a useful thing to find. But more importantly, the x-intercepts, right? So the x-intercepts are just the zeros of the numerator of your function, right? They're the zeros of p. If f of x is p of x over q of x, then the x-intercepts are just the zeros of p. So you set the numerator equal to 0 and solve for x. Those are your x-intercepts. The other thing you probably did is you found vertical asymptotes. Now, not every rational function has a vertical asymptote. Some of them have 0, some of them have 1, some of them have several, right? You could have 2 or 3 or 4 vertical asymptotes, or any number of vertical asymptotes. But the way that you find them is the vertical asymptotes are the zeros of the denominator, q. And by zeros, I mean the real zeros, okay? So you could have a non-real zero, but that non-real zeros are not going to show up in the graph of the function in any way, okay? So the vertical asymptotes are the real zeros of your denominator. The x-intercepts are the real zeros of your numerator, okay? So you probably did those two things, and then the third thing that you did is you probably looked at the end behavior of your function, which now that we have calculus, we know that what we're really talking about is the limit as x goes to positive infinity of the function and the limit as x goes to negative infinity of the function. And what that end behavior tells us is what kind of asymptotic behavior we have. All rational functions. So not all rational functions have vertical asymptotes, but all rational functions do have either a horizontal asymptote or an oblique asymptote, right? So a horizontal asymptote, you're going to find when you take the limit as x approaches infinity or as x approaches negative infinity of the function, if you approach some finite value, well, that's just a horizontal asymptote, right? And so the function has a horizontal asymptote. If you don't approach some finite value, then you have what's called an oblique asymptote. And the way that you find oblique asymptotes is you actually just perform the long division. It turns out that with rational functions, and again, I'm assuming that you know all of this stuff, and so I'm just helping you remember this information. Okay, if this is all new information to you, then you've got some catching up to do, and again, you've got to let me know, right, so I can help you catch up. But anyway, as you may recall, it turns out the only way you're going to have an oblique asymptote if you're dealing with a rational function is if the degree of the numerator is greater than the degree of the denominator. Okay, that's when you end up having an oblique asymptote, and you find that oblique asymptote by performing long division. Okay, so I'll give you some examples of this as we go forward, but these are kinds of things that you did. Now, in addition to all that, doing all of that stuff usually gives you some framework for being able to graph your function. Let me draw you a picture of what I'm describing. So let's say that you've gone along, you've found your vertical asymptotes. Maybe you have a vertical asymptote here, and maybe you have another vertical asymptote there, and then you've determined from the end behavior of the function that you've also got this horizontal asymptote here. Okay, and then in addition to that, you've found some intercepts, right? So you know that you've got like an x-intercept here, and then maybe you've got an x-intercept here. Okay, and those are your only x-intercepts, right? So this is usually enough framework for you to be able to graph the function. Like, for example, I know that since I have an x-intercept here and a vertical asymptote there, whatever function I have is going to be trapped down in this little quadrant, right? It's got to look, something like that. Now, it could be that this function does cross its horizontal asymptote, right? A function can never cross a vertical asymptote, because if it crossed a vertical asymptote, well, then it would fail the vertical line test, right? And it wouldn't be a function. So functions are never going to cross vertical asymptotes, but they could cross horizontal ones. So you could have a scenario maybe like this, right? Where the function sort of crosses its horizontal asymptote, but then comes back down. So in your pre-calculus days, you would have to consider that situation, and you would have to see, well, if I set the function equal to the horizontal asymptote and then solve for x, do I get a solution? Because if I do, then that tells me that the graph crosses its horizontal asymptote at that location, right? So that is a possibility. We're not going to worry about that in calculus, because notice that if that happens, right, if this graph crosses its horizontal asymptote, then it's going to have an inflection point, right? It looks like the inflection point takes place right there, right? But it's going to have an inflection point where you go from being, in this case, concave down to concave up. Okay, so we're not going to worry about if it crosses its horizontal asymptote. We'll know if it crosses its horizontal asymptote based on whether or not you've got, inflection points. Okay. So, but that was one consideration that you had to worry about in pre-calculus, and we're not going to worry about it so much anymore. The same thing sort of happens here, right? It's like, you know that you've only got one x-intercept. Okay, so either the graph has to look like this, maybe, or maybe it does this, right? And you're not quite sure which one happens. You might be able to narrow that down by finding the y-intercept. That would kind of give you some information. But and then you also have some information about, you have this 0, but was it a multiplicity? Was it an odd multiplicity or an even multiplicity? If it's an even multiplicity, then we have the bottom case, right? Because if it's an even multiplicity, then it touches but does not cross the x-axis, right? So it would have to do that. If it's an odd multiplicity, then it's going to cross right through, and you'd have the second case. Notice though that if you do have the second case, then this graph is crossing its horizontal asymptote. But notice again that you're gonna, if that is the case, you're gonna have an inflection point somewhere. Okay, so you're gonna have an inflection point somewhere. So once again, we're not so concerned about whether this crosses its horizontal asymptote, because we will know that based on whether or not the graph has any inflection points. And so we'll just use calculus to determine that. But another thing to think about is this. If you look at what's happening as you approach your vertical asymptotes, so like in this case with what I've drawn, it looks like we're going to negative infinity and to negative infinity. Because, maybe I should say this, there's a third option, right? Maybe the graph is actually coming down and going down that way, right? So the only way to really know that is to determine, well, what's going on close to this vertical asymptote? What am I approaching, positive or negative infinity, as I approach from the right and as I approach from the left? So we're just going to apply calculus techniques to figure that out. So if you know that you're approaching, say, negative infinity here and negative infinity there, and if you've only got this one intercept, well, then you know it's got to look something like that, right? Or even if you had two intercepts, but you know that you're approaching negative infinity there, negative infinity there, then it's got to go up and do something like this, right? And then come back down. By the way, that'll tell you that you've got a relative maximum at that location. So the point I'm trying to make is that the calculus will give you a lot of additional information that you didn't have available to you in pre-calculus, and it makes a lot of the work easier. So instead of going out and trying to find if the thing crosses its horizontal asymptote, you really don't need to worry about that. That's taken care of with inflection points. In order to determine exactly how high or how low this thing peaks, you don't have to worry about that. That's taken care of by looking for relative extrema. Okay. Whether this thing crosses here in the middle, whether it crosses its horizontal asymptote, again, doesn't matter. If you can look at the limits, as you're approaching this vertical asymptote, look at what's happening from the left and from the right, then you don't need to plug in test points or whatever you did back in pre-calculus, right? You can just use calculus to figure out what's going on. And then finally, over here in this kind of third quadrant, you don't have any x-intercepts, and you know that this is a horizontal asymptote, which means the graph has to get closer and closer to it the further out you go. So if you were trapped down here, that would mean that you would have to cross the x-axis at some point, and you know that doesn't happen. So that can't be the case. It must be something like this, right? It must be something like this. And once again, it could be the case that it sort of crosses its horizontal asymptote and then comes back down or whatever, but in that scenario you would have some inflection points, right? So once you've done your due diligence of finding x-intercepts, finding vertical asymptotes, kind of determining end behavior, that gives you a lot of framework to have some sense for what's going on. And so then, just to get additional understanding of the function, we'll do first derivative test to find relative extrema, right? Second derivative. Second derivative test, I guess, would also be to find relative extrema. But I guess what I mean is we'll look at the first derivative to find relative extrema. We'll look at the second derivative to find critical points, if there are any. and see if those critical points are then inflection points, right? And that'll really give us all the information that we need in order to be able to graph these rational functions. Okay, so without further ado then, let's actually look at some concrete examples. So let's graph some stuff. You may wonder, I guess, like, well, why do we need to know how to graph? We could just plug this into Desmos, and you're right, but let's say that you're actually interested in the exact value of a particular relative extrema. You have to have calculus in order to find it, right? Or if you needed to know the inflection point, it's like Desmos might just have an approximation for what that value is, right? In order to actually find the exact value of that inflection point, you have to rely on calculus. And then, of course, there's the idea that, well, someone has to program Desmos, right? So they've got to know about this kind of stuff. Anyway, so let's graph. Let's graph y equals 2x squared minus 8 over x squared minus 16. Okay, so I'm going to kind of walk you through the process as far as I see it. If you want more like step-by-step directions on like step 1 do this, step 2 do that, you can look in the book. I think they have some good suggestions there. But here's how I'm going to approach this. I'm going to do the standard kind of pre-calculus thing. I'm going to find the intercepts, I'm going to find the vertical asymptotes, going to look at the end behavior. And then in addition to that, I'm going to look at some derivatives and try to figure out where my relative extrema are, where my inflection points are. Okay, and then based on that information, I'll have some good framework to be able to graph this function. So let's get to it. So as far as finding intercepts and asymptotes are concerned, really, if you can factor this thing, then life's going to be a lot easier for you. So I think when this thing is fully factored out, we end up here, right? Okay. And so zeros from the numerator give you your x-intercepts, right? So we've got an x-intercept at positive 2 and at negative 2. Zeros from the denominator tell you where you have vertical asymptotes. So we've got vertical asymptotes at positive 4 and at negative 4. Okay? And again, I'm kind of imagining, I guess, setting these things equal to 0 and then solving for x, which is why I'm flipping the signs, right? Like if you solve x minus 2 equals 0 for x, you're going to get x equals positive 2. And here you're going to get x equals negative 2. Here you're going to get x equals positive 4. And here you're going to get x equals negative 4. Okay, so so I know that I've got x-intercepts at positive 2 and at negative 2. And then I know that I have vertical asymptotes at x equals 4 and at x equals negative 4. So this, I suspect, is a pretty symmetric graph, because look at your vertical asymptotes, your x-intercepts, right? They're all symmetric with respect to the y-axis. In fact, if you plug in a negative value for x, you're going to get the same answer as if you plug in a positive value for x, since these are both just being squared. That tells you that y is an even function. So it is going to have symmetry, perfect symmetry across the y-axis. So that's kind of good information to keep in mind. It's not totally necessary to be able to graph the function to know that it's got that symmetry, but it's nice to know it, kind of going into things. What about end behavior? So as far as end behavior is concerned, right? Another way to say this is, does this thing have a horizontal asymptote or does it have a vertical asymptote? Or sorry, does it have a horizontal asymptote or an oblique asymptote? Well, so to determine the end behavior, first of all, if the degree of the numerator is greater than the degree of the denominator, that's when you have oblique asymptotes. And you find them by doing long division. That's not the case here, though, because the degrees are the same. So the end behavior is really just, it's the limit, right, as x goes to infinity, or as x goes to negative infinity of the original function, right? Maybe just for shorthand, I'll just call it f of x, right? So what's the limit as x goes to positive infinity? Well, it's just going to be the ratio of the leading coefficients, right? Because this is a polynomial by a polynomial. So it's going to be 2. It's going to be 2. And same thing's going to happen, I think, as x goes to negative infinity, right? It's going to be the ratio of the leading coefficients. So that's going to be 2. So we've got, in other words, we've got a horizontal asymptote at y equals 2. Okay, so this is all good information. I suppose I could find my y-intercept as well. So I've got my x-intercepts there. My y-intercept, I get my y-intercept by plugging in 0 for x, right? If we plug in 0 for x, we get negative 8 over negative 16. That's 1/2. So 0, 1/2 is my y-intercept. Okay, so I've got all kinds of good information. I could start to graph some of this, and I'll leave some space to do my derivative work, but I can start to graph some of this. So I've got vertical asymptotes at 4 and negative 4. I've got x-intercepts at negative 2 and positive 2. I've got a y-intercept at 0, 1/2. I might regret making this graph too small or something, but this is what I know so far. Oh, and I've got a horizontal asymptote at y equals 2. Okay, so even without the calculus, I mean, just based on this information, I'm gonna guess that, right, we've got this sort of almost upside down parabola looking thing down here, and then I'm gonna guess that we've got these little corner pieces up in the right hand corner. I don't think we would have anything down here, because that would sort of imply that you're gonna have x-intercepts out here, and we know that we don't, right? So I think it's gonna look like this, these little corner pieces, and then this little upside down parabola. But to sort of verify that, we could look for relative extrema, we could look for inflection points. So let's do that. So again, I'm kind of changing the name here to f instead of y. I'm calling it f of x. And then I can just say, so f prime of x, right, the derivative, is going to be low d high minus high d low over low squared. Okay. All right. So that's interesting. This is interesting. So a couple things. As far as finding critical points is concerned, critical points, you're going to get critical points whenever the derivative is undefined, right? So wherever the function is not differentiable. And you're also going to have critical points wherever the function is equal to 0. So we want to, set this equal to 0 and solve for x. Maybe we can clean this up a little bit. So we're going to get 4x cubed minus 64x minus 4x cubed, oh that's nice, minus 16x, but it's minus a negative, so I'm going to say plus 16x. That cleans up very nicely, right? Okay, good. So 64 minus 16 is what? So 64 minus 6 would be 58, so 48, so negative 48. Oh, I should have known that, right? Anyway, this is negative 48x over x squared minus 16 squared. Okay. So you're gonna so the function is not differentiable at 4 and at negative 4. But guess what? The function isn't even defined at 4 and negative 4, right? So 4 and negative 4 are not even in the domain. They're not even in the domain of the function. So of course they're not going to be differentiable there. And that's not really any new information for us because we already know that we've got vertical asymptotes at 4 and negative 4. So we don't really get any useful information about the fact that the function's not differentiable at 4 and negative 4. But we do get some useful information from the fact that the function is 0 whenever x equals 0, right? If x equals 0, right? If you set the numerator here equal, or if you set the entire function equal to 0 and then solve for x, you're going to get x equals 0, right? That's the only solution. So, so we know that at x equals 0, we've got a critical point, right? So f prime of x equals 0 when x equals 0. So x equals 0 is a critical point. So to determine if that critical point is a maximum or a minimum, you can do one of two things. You can either make a sine chart, right, and use the first derivative test, or you can go ahead and take the second derivative of f, right, and use the second derivative test. Okay. Plug in 0, your critical point, to the second derivative, and if the second derivative is positive, well then you know that the function is concave up, and in which case you would have a relative maximum, or sorry, a relative minimum. If it's negative, then you're going to be concave down, in which case you have a relative maximum. I'm kind of inclined to just do the first derivative test because I kind of want to have some idea about where this function is increasing and where it's decreasing anyway. And in fact, when I make my sine chart, I'll include these asymptotes as well, these vertical asymptotes, so that I have some sense for what's going on. So let me go ahead and make a sine chart. So I'm going to go from negative infinity to negative 4, and then from negative 4 to 0, because that's where I have a critical point, and then I'll go from 0 to 4, and then I'll go from 4 to positive infinity. And let's plug these things into f prime so that we have some idea about whether the function is increasing or decreasing on these various intervals. Okay, so from negative infinity to negative 4, if I plug in like negative 5 to f prime, right, to the derivative, I'm going to have a negative in the numerator. The denominator is going to be positive always because I'm just squaring this stuff, right? So I'm going to have a negative, negative. That'll make a positive overall. If I plug in something between negative 4 and 0, like negative 2, I think I have the same situation still, right? Negative 2 is going to give me a negative in the numerator, a positive in the denominator, but I'm negating the whole thing, so it's still just going to be positive. But if I plug in a positive number between 0 and 4, like 2, well, now the numerator becomes positive, and that makes this whole thing negative. And then here, I think it's still going to be negative for the same reasons, right? So what that tells me is that so I'm increasing until I get to 0, and then after 0 I'm decreasing. That means I have a maximum at 0, which is exactly what it looks like I should have. Okay. Meanwhile, the fact that I'm increasing up here if I were increasing and somehow I were below my horizontal asymptote, then at some point I would have to cross the x-axis, right? And that doesn't happen over here. So that just confirms my suspicion that this is what I have going on up in this quadrant, and that this is what I have going on sort of in the middle space. And then up from 4 to infinity, I'm decreasing. So that tells me that I must have this kind of thing going on. I guess the only thing I'm not certain of, and I guess I shouldn't have drawn this in pen, because I am still uncertain about whether or not these things ever cross their horizontal asymptotes. That is possible. So to determine that, I should really look for inflection points, which means I need to take the second derivative now. And I'm kind of running out of space, so I'm going to have to sort of carve out some space on this side of the page. But let's go ahead and take the second derivative, f double prime. Okay, so that's going to be, I'm going off of this function here. So f double prime is going to be low d high negative 48 minus high negative 48x d low, and I've run out of space. You know what? I'm going to cheat. Just put another page next to it so that I have room to write the derivative of the bottom. So that's going to be, so we're going to have to apply chain rule here, right? So it's going to be times 2 times x squared minus 16 to the first power times the derivative of the inner function, which is 2x, right? So times 2x. Okay, all of that over low squared again. So I'm going to have x squared minus 16 to the fourth power, I believe. Okay. So there's f double prime. Man, I wonder how this thing cleans up. I can at least factor out an x squared minus 16. That'll make things a little bit easier in the numerator there. So I'm going to factor out an x squared minus 16. I would be left with negative 48 times x squared minus 16. And then 2 times 2 is 4. So then minus, well, really I would say plus 48x times 2x. Okay, I can clean that up a little bit more as well. 48x, well, first of all, I can distribute the negative 48, right? So I can call this x squared minus 16 times negative 48x squared. 48 times 16 768, right? So plus 768, and then 48 times 2 I think is 96, so we say plus 96x squared. Oh, that cleans up pretty nice, I think. Let me take it one more step. So I'm going to try to squeeze it in here. X squared minus 16. Okay, 96 minus 48 is going to be 48. And then I know that 48 is a factor of these two numbers. So I'm just going to factor out the 48. Maybe I'll put it out here in front. 48. And then what would I be left with? Well, I would be left with x squared, right? Because 96 minus 48 is 48, and I factored it out. And then 768 divided by 48 would just be 16. So it's x squared plus 16. That's interesting. I feel like I'm missing something. Oh, and I could cancel off one of the x squareds minus 16, right? And just get x squared minus 16 to the third down there in the denominator. But what am I missing? So this example comes from your book, and I'm looking at their second derivative, and they're coming up with 3x squared plus 16. So I'm missing a 3 here somehow. When did that happen? Maybe it was here. This should have, yep, this should have been a 4x. I apologize. And so instead of 96, I would have had 48 times 4 is 192. And then 192 minus 48 would be 144. And then if I take out the 48, so 144 divided by 48 is 3, sure enough. Okay, so I should have had a 3 there. Oh, okay. But now, this cancels one of those. So really, I'm going to write this over here now. Really, at the end of the day, f double prime of x is 48 times 3x squared plus 16 divided by x squared minus 16 to the third. Very good. Now, what does that tell us about inflection points? It tells us that we don't have any. Because you're going to get inflection points wherever you have zeros, wherever the second derivative is equal to 0. And that would happen at that would happen if the numerator is equal to 0, right? But if you set the numerator equal to 0 and solve, you're going to get non-real results. So we know that there are no inflection points. Okay, and since there are no inflection points, that means that these things, they never cross their horizontal asymptote. So this really is the correct picture, right? This is almost exactly what the picture is going to look like, and we can verify it by looking at this in Desmos. So look at f of x equals, this was 2x squared minus 8, divided by x squared minus 16. And there you go, right? That's almost the exact picture that we drew. Okay, so that's that one. Let's move on. Okay, so let's do another rational function. I think I'll just give you one more of these because, as you can see, it's a time-consuming process. I've already been talking for probably close to 40 minutes now. But anyway, let's do f of x equals x squared minus 1 over x cubed. Go ahead and give the video a pause and see if you can work that one out on your own. Okay, so let me walk you through this one. Okay, so again, I'm going to start off just by factoring everything. X plus 1, x minus 1 over x cubed. That gives me a lot of good information. That tells me that I've got x-intercepts at -1 and at +1. right? Because the x-intercepts come from the numerator. In the denominator, I've got a vertical asymptote at x equals 0. As far as y-intercepts are concerned, now this is interesting. I don't have any y-intercepts, right? Because if I plug in 0 for x, then I just get 0 over 0, which is undefined. So I've got no y-intercept. Okay, so that's very interesting. Well, and actually another way to tell that you have no y-intercept is that you've got a vertical asymptote at 0, right? So how could you have a y-intercept? Functions can't cross vertical asymptotes. Okay, so that's good. As far as end behavior is concerned, again, the degree of the numerator is less than the degree of the denominator, so I know that I don't have an oblique asymptote. I must have a horizontal asymptote then. And what's it going to be? Well, let's check it out. Limit as, we'll say, x goes to positive infinity of f of x. Well, degree of the numerator is less than that of the denominator. This thing's going to go to 0, right? It's going to go to 0. And the same thing is going to happen if x goes to negative infinity. So in other words, I've got a horizontal asymptote at y equals 0. Okay, so a vertical asymptote at x equals 0, a horizontal asymptote at y equals 0. That's kind of interesting. I'm going to start to draw what I know. Maybe I'll do it at, well, no, that's fine. I was going to say maybe I'll do it at the bottom of the page so I have more space, but it doesn't matter. I'll put it here. Okay, so here's what I know so far. Okay, that's all I know so far. Something that's interesting is that notice that this is a case where the graph crosses its horizontal asymptote. You know that because its horizontal asymptote is the x-axis, and it's got two x-intercepts. So you know that this thing crosses its horizontal asymptote. And that's really all we know. So a couple possibilities is that maybe this thing kind of looks like, I don't know, maybe something like this. Although it's not going to get further away from the horizontal asymptote, is it? Like it's got to come back up, which means there's got to be some inflection points here. So maybe it looks like that. Then again, maybe it's doing just the opposite, right? So maybe it's going down, right? Or maybe one side's going down and the other side's going up. I mean, we really don't know at this point. I think the only way to figure it out, well, there are a couple ways you can figure it out. I mean, you could just plug in some points and see what's going on. But let's use some calculus, right? Let's use some calculus to see if we can figure out what's going on. So take the first derivative. It's going to be low d high minus high d low over low squared. And let's see if we can clean that up a little. 2x to the fourth minus 3x to the fourth plus 3x squared. Okay, so that's going to be a negative x to the fourth plus a 3x squared. Maybe I'll rewrite that as 3x squared minus x to the fourth. Oh, we can cancel off some of those x's, right? We could take out an x squared, and then we would get 3 minus x squared over x to the fourth. Okay, well that's not bad at all. Okay, as far as critical points are concerned, well, we would have a critical point at 0, except that the function's not even defined at 0. We would also get critical points at plus or minus square root of 3. right? If we set this equal to 0, 3 minus x squared over x to the fourth equals 0 implies 3 minus x squared equals 0 implies 3 equals x squared implies x is plus or minus root 3. Okay, so critical points at plus or minus root 3. Let's go ahead and take the second derivative. And then we can use the second derivative to decide if these are maxima or minima, or maybe neither. But also, second derivative will tell us if we have inflection points, right? If and where we've got inflection points. Because that gives us information about concavity and stuff. Okay, so let's find second derivative. Second derivative is going to be low d high minus high d low over low squared. Do you ever get to the point in the middle of a math problem where you're like, I don't want to do this anymore? Because it gets so nasty sometimes. I don't know, it's kind of fun though. Let's see, negative 2x to the fifth, and then we're going to have negative 12x cubed, and then plus 4x to the fifth. So again, I think this one will clean up pretty nicely. So we're going to have 2x to the fifth, a positive 2x to the fifth, minus a 12x cubed. We can take out an x cubed, right? Actually, we can take out a 2x cubed. We would be left with 2 times x squared minus 6 over x to the fifth. Okay, good. So again, we would have an inflection point at 0, except that the function is not even defined there. We're also going to have possible inflection points at plus or minus square root of 6. Okay. But more importantly, to decide if plus or minus root 3 are maxima or minima, we can plug these into the second derivative and see what we get. So if I plug in positive square root of 3, I'm going to get, so let's say f double prime of root 3. I don't really care about the actual value. I only care about the sign of this answer. Right? So it's going to be 2 times positive, right, or actually a negative number. Square root of 3 squared is 3. 3 minus 6 is negative. So it's going to be 2 times the negative divided by positive, right? Square root of 3 to the fifth power is going to be positive. This is going to be negative. That's interesting, right? That tells me that at x equals square root of 3, f of x is concave down. Square root of 3, by the way, is like 1.7. So square root of 3 would be somewhere between 1 and 2, like 1.7. And f of x is concave down there, which tells me that square root of 3 is a maximum, right? So, and maybe I can get the y coordinate. So to get the y coordinate, I plug that into the original function, right? So root 3, and then if I plug in square root of 3 to the original function, that's going to be 3 minus 1 is 2. 2 divided by square root of 3 cubed. So it's going to be 2 over root 3 cubed, which is about, square root of 3 is 1.7. 2 over square root of 3 cubed. Is about 0.5. 4. Okay, so that is a maximum. It's a relative max. Okay. Okay, what about negative root 3? So f double prime of negative root 3. If I plug in negative root 3, I'm still going to get a negative here, so it's going to be 2 times a negative divided by, well, negative root 3 to the 5th is going to be a negative, so that's going to be positive. That tells me that at negative root 3, so at negative root 3, which is, you know, somewhere here between negative 1 and negative 2, I'm concave up, which means that negative root 3 is going to be minimum, right? So therefore, root 3, negative root 3 f of negative root 3, which is negative root 3 2 over negative root 3 cubed, which is going to be approximately negative 1.7, negative 0.4, is a minimum. Okay, well that's cool. Let's put those points on there. So I've got 1.7, 0.4, maybe something right about there, and negative 1.7, negative 0.4, maybe somewhere right about there. This is a relative maximum. So that tells me that I reach a maximum and then I start to decrease, right? So the function must look like this. It must look like this. And then on down here, this is a relative minimum. So that tells me that the function must be doing something like that. Whoops, sorry. So you weren't seeing what I was looking at, but I was saying this is a maximum, so the function must do something like this. This is a minimum, so the function must do something like that. Okay. So, and that's really all I need, right? Like, if I wanted to, I could find the inflection points, because I know that, you know, here I'm concave down, but I change to be concave up. And that must be happening at square root of 6, right? Right, this is the second derivative, so I've got a change in concavity at positive square root of 6. Positive square root of 6 and at negative square root of 6. So the concavity is changing at positive square root of 6 and at negative square root of 6. I'm not going to take you through all the gory details there, but yeah, so I've got a change in concavity at plus or minus root 6. What else could we say about this? If I wanted to be certain that this thing is going down and this thing's going up, you know, I could look at the limit as x approaches 0 from the right. I could look at the limit as x approaches 0 from the left and kind of figure out, you know, what's going on there. But I suspect this is the way that it's going to look. Let's take a look at what Desmos has to say about this. X squared minus 1 over x cubed. Yep. Alright, that's more or less what we drew. Okay. So I've been going for how long now? 53 minutes. I think I'm gonna split this lecture into 2 different videos. Okay, so let me just finish up what I have to say about rational functions real quick. We won't work these out in detail, but I just want to show you, like, if you had something like f of x equals x squared plus 1 over x, where the degree of the numerator is greater than the degree of the denominator, this is when you have oblique asymptotes. And to find the oblique asymptote, you just do division, right? In this case, it's easy, right? You can just say this is x squared over x plus 1 over x, and that's just x plus 1 over x. And then if you think about what's happening when x gets really, really big, this part's going to 0, which means that the function is going to behave more or less, when x is really far away from 0, this function is going to behave more or less just like the straight line f of x equals, right, y equals x. So your oblique asymptote is the line y equals x. And so when you go to graph the function, right, you're going to have a bunch of things going on. Like, for example, you're going to have a vertical asymptote at 0, right? So you have a vertical asymptote at 0. But then you also have this oblique asymptote at the line y equals x. And so you have this kind of situation. And I don't know exactly what this thing looks like because I'd have to, go through the process of doing the work. But it's like, you probably have a scenario like this. Because you don't have any x-intercepts, notice, right? The only solutions in the numerator are non-real. So you know you're not crossing the x-axis. Anyway, so your graph probably looks something like that, is what I would assume it ends up looking like. Okay, but the point is, the main thing I wanted to point out is the oblique asymptote. And let me just give you one other example of that, right? So let's say instead that you had, x cubed minus x squared minus 8 over x minus 1. Now, again, the degree of the numerator is greater than the degree of the denominator. And that means you're going to have an oblique asymptote. To find it, you would have to do long division, right? Because this one, unfortunately, you've got a binomial in the denominator, so you can't just kind of split it the way that we did the previous one. You'd actually have to say, x minus 1 into x cubed minus x squared plus 0x minus 8, and then go through, the long division, right? Anyway, I'm not going to finish the problem. But what you're going to end up with when you do that long division is up here you'll end up with some kind of quadratic. And so that tells you that your oblique asymptote is a quadratic equation in that case. And let's just look at that one in Desmos real quick so that you get some sense for what I'm talking about. Okay, and I might have to zoom out a little. Okay, yeah, so you zoom out a little and notice that, well, it's maybe a little difficult to see, but you've got a quadratic asymptote here. Let me look it up in the book and see, because I don't know if they actually did this problem. Yeah, so apparently the oblique asymptote is the curve y equals x squared, just like the standard parabola. Yeah, and sure enough, in fact, let me change this to a dotted line so that it's the asymptote, right? So the red stuff is not part of the graph, it's just the asymptote. But yeah, look, as you zoom out, the green stuff, the further away you get from 0, the more the graph looks like this quadratic curve. And of course, there's interesting stuff happening in the middle, but the end behavior is like the graph of y equals x squared, and this is what you would get if you actually did the long division. Okay, or maybe you can factor this thing and then just cancel something. I don't know, but anyway, that's the idea there. Like I said, I'll stop the video there because, man, I've been going for almost an hour, and then I'll finish up this section in another video.